Hello and welcome to a multi-part series where we will build a first-person controller in Unity. We will start from scratch, so we're not using any pre-built assets, and by the end we will have a fully functional character controller. In this episode, we will focus on implementing the basic features, such as controlling the camera with the mouse and basic movement using the WASD keys. So let's get straight into it. First of all, I'll create an empty game object called player, and I'll attach to it a character controller. This is the component which will handle the player's movement and collision detection, and as part of that, it introduces a capsule-shaped collider with a height of 2 units by default. Taking these units to be meters, this is roughly the height of a normal human, so for now, we'll leave this value alone. Making sure that the transform gizmo is positioned at the pivot of the game object, I will position the capsule 1 unit higher on the y-axis. This way, the game object's pivot point will sit at the base of the capsule instead of its center. This just makes it easier to position in the scene. I will create a new camera as a child of the player object, and since the capsule is 2 units high, I will offset the camera upward by 2 units so that it's positioned at the very top of the capsule. I'll then position the player object so that it starts at the origin of the scene, though you can position yours wherever it's most convenient. One more thing, the character controller will pass through meshes that have no colliders on them, so make sure to attach colliders to any objects in your level that the player should touch. And yes, this includes the floor. Otherwise, once we start to apply gravity a bit later on, you'll be in for a nasty surprise. Let's create a script called player controller and then attach it to the player object. I will then open this up. The first thing I'd like to do is get the camera movement working with the mouse, so we will need to access the transform of the camera. In the class, let's create a field of type transform called player camera. Then in the editor, with the player object selected, drag the camera object from the hierarchy into the player camera slot of the script. I'm also going to create a dedicated method for all of the mouse look functionality, and I will call this from update. So, whenever the mouse cursor moves vertically on the screen, we will want this motion to influence the pitch of the camera so it looks up and down. To achieve this, we will need to pivot the camera on its local x-axis. You may think then that the horizontal motion of the cursor would rotate the camera on its up vector, but in fact we rotate its parent object on the up vector instead. Since the camera is a child of this object, it will still rotate with it, but the advantage to this approach is that the forward-facing vector of the parent object will remain aligned to the direction that the camera is pointing. As we'll discover later on, this is extremely useful when we're implementing movement for the player. Finally, by combining both of these cursor movements together, we have a fully controllable camera look system. So, let's first retrieve the vertical and horizontal cursor motion, also known as the mouse delta. Let's create a vector2 object called mouse delta and set this to a new vector2. We will store in its x component the horizontal mouse delta, which we can obtain by calling input.getAxis and passing in the string mouse x. Then for its y component, we will store the vertical delta, to which we call the same function while passing in mouse y instead. Starting with the horizontal motion of the cursor, the script that we're working in currently is already attached to the parent object of the camera, so we can easily access its transform directly and instruct it to rotate on its up vector using the horizontal mouse delta. Testing this out, it behaves correctly, but the rotation speed is a bit sluggish. So I will create a float field in the class called mouse sensitivity, and I'll give it a default value of 3.5. When rotating the object, we then multiply this value with mouse delta.x, and now we can use it to control the speed of rotation. For me, a sensitivity of 3.5 seems roughly correct, but feel free to play around with this value until you have something you're happy with. So the next thing is the vertical motion of the cursor that rotates the camera on its local x-axis. Before we go any further, there are a couple of things to consider. The first thing to remember is that the vertical mouse delta is negative when the cursor moves down and positive when it moves up. However, the camera's X rotation is required to increase to pitch downward and decrease to pitch upward. So we have an inverted y-axis, and in the case of this tutorial, we don't want this. So we can simply invert the vertical mouse delta to get the correct result. The second thing to consider is that if we look too far up or down, the camera will flip upside down. As a result, we will want to clamp the pitch of the camera so it isn't able to look any further than 90 degrees upward and 90 degrees downward. It's useful to note that the X rotation of the camera is 0 when looking directly forward, negative 90 when looking directly up, and 90 when looking directly down. So in the class, let's create a float field called camera pitch. This will keep track of the camera's current X rotation. I will give it an initial value of 0, meaning that the camera will begin looking directly forward. In the mouse look function, we will want the vertical delta to influence the value of camera pitch. Now, we could simply add the delta to the rotation like so, but we can be clever here and use subtraction instead, which has the effect of applying the inverse of the delta, which solves the issue with the inverted y-axis. We can then multiply this by the mouse sensitivity value like we did earlier with the horizontal mouse delta. You'll then want to make sure to clamp the value of camera pitch between negative 90 and 90, which makes sure that the camera remains within the acceptable angular range as to not flip upside down. Finally, we can set the camera's local Euler angles such that it rotates around the right vector by the camera pitch. And testing this in the scene, we now have a fully controllable camera which we can look around with. The only other thing, we will want to confine the cursor to the center of the screen and make it invisible. We can set this up quite simply. In the class, create a Boolean field called lockCursor, which I will set to true by default. And in the start method, we check to see if this Boolean is true, and if so, then we assign cursor.lockState to cursorLockMode.locked. This locks the cursor to the center of the screen. And then we can assign cursor.visible to false to make sure the cursor remains invisible. And now we can look around without the cursor getting in the way. The next thing I want to cover is the movement of the player, which includes walking around with the WASD keys and gravity. So let's set up a dedicated function for this and call it from the update method. To begin with, let's focus on the forward and backward movement using the W and S keys. By default, Unity handles this input via the vertical input axis, which can be thought of as a value that sits on a one-dimensional axis spanning from -1 to 1. When there are no keys currently being pressed, the value remains in a neutral position at 0. However, it's pulled upward toward 1 when the W or up arrow key is held down, and it's pulled downward toward -1 when the S or down arrow key is held. In order to convert this into a direction that the controller can move in, we can multiply this value with a vector that represents a direction in 3D space. This has the effect of scaling the vector by the value, such that 1 would correspond with the original vector, 0 would squash the vector into an infinitely small point, and -1 would result in the inverse of the original vector. So Once multiplied with a vector, we can see that this value can represent both a forward and backward direction, including no direction when it's 0. But in this example, the vector is stationary. When the player controller rotates, the direction considered to be forward and backward is dependent on the orientation of the camera. But remember, I mentioned earlier that we should rotate the parent object of the camera on the up axis. This way, the forward vector of the object always points where the camera is pointing. So, if we were to scale this particular vector using the vertical input axis, we can see that it behaves identically to the previous example, but it now accounts for the orientation of the player as well. This is ideal since we now have a way of calculating the correct direction to move in. There's also a horizontal axis, which behaves identically to the vertical axis, but for the AD left and right arrow keys. And of course, this will be used to scale the right vector of the player object. So this axis will control the amount at which the controller moves sideways. In all of these examples, the value has smoothly transitioned between the three values on the axis. But in the code, we want to access the raw value of these axes, which is simply the value when no smoothing is applied. In other words, it will snap instantly to one of the 3 points on the axis, depending on the buttons that are pressed. The reason we need the raw value is so that we can normalize the direction vector, which we will discuss shortly. So let's grab the axes to begin with, which I will store in a vector2 object, much like the mouse delta. I will store the horizontal axis in the x component, and I can get this value by calling input.getAxisRaw and passing in the string horizontal. And for the y component, I can call the same function while passing in vertical instead. Visualizing the player controller from above, we can overlay the vertical and horizontal axes on top of each other. Because we're accessing the raw value of these axes, there are a total of 9 possible directions we can move in. These include forward, backward, left, right, all of the diagonal directions, and of course, no direction. If we were to measure the length of the forward, backward, left, and right vectors, all of these would equal 1, which is ideal since we can multiply a speed value with these directions and get a nice result. Likewise, no direction is fine since it's just a 0 vector, so multiplying this by a speed value results in 0 anyway, which is stationary. However, if you were to measure the length of any of the diagonal vectors, you'll find that they're approximately 1.4 units long. So we'd actually move slightly faster when moving diagonally, which isn't preferable. The solution to this is to normalize the vector, which preserves its direction but limits its length to 1. So when the controller moves diagonally now, it will move at the same speed as it would if it were moving on a single axis. And in the code, this is quite simple to achieve. We just call the normalize function for the input direction vector, and this will normalize the vector. So remembering the visual from earlier of how the vertical and horizontal axis are applied to the forward and right vector of the player object, I'm now going to define a velocity vector to which I will set it to the forward vector of the player object scaled by the vertical axis, added to the right vector of the object scaled by the horizontal axis. Finally, to customize the speed at which we move, I will set up a simple float field in the class called walk speed, set this to 6 by default, and then multiply it with this whole expression. Now remember that the character controller will handle the movement and collision, so we'll want to apply the velocity value to this component. I will create a new field in the class of type character controller, and I'll call it controller. In the start method, we can then set this field to the attached character controller. To apply the velocity, we can then call the controller's move function, and we pass in the velocity value multiplied by time.delta time. Now, although the controller can move at this point, the movement isn't smoothed, so the controller will start and stop moving instantly, which is quite jarring. Of course, this is because we're using the raw value of the vertical and horizontal axes. So what we want to do is smooth the input direction. Since we've stored the raw values inside a vector2 object, we can use the function vector2.smoothDamp. This allows us to smoothly transition from one vector2 value to another. The function has 4 parameters that we care about: the current vector, which is the vector that we're smoothing, the target vector that we're smoothing toward. Then we need to pass in a reference to a vector2 object. This is a reference because the function will modify this value and use it to store the current velocity, which it will need to access again when it's called during the next frame. Finally, smooth time is just the approximate time it will take to smooth from the current to the target vector. The other 2 parameters are optional and we won't be using them, so we won't need to worry about these. So let's set up the smooth time as a float field called move smooth time. I may as well make this a range slider between 0 and 0.5, then give it a default value of 0.3. Next, we will want to declare a vector2 that stores the current direction and the current direction velocity. Now in the update movement method, the input direction vector now becomes the target that we want to smooth toward, so I'll rename it to reflect this. So let's set the current direction to vector2.smoothDamp, passing in the current direction as the first argument, then the target vector that we're smoothing toward. Then we can feed in a reference to the current direction velocity, and finally we will pass in the smooth time value. Now we want to use the current direction vector to define the velocity, since this is the vector that's being smoothed. I'd also like to be able to smooth the camera rotation as well. In the class, create a mouse smooth time variable. By default, set it to 0.03. Then create another field called current mouse delta and current mouse delta velocity. Inside the mouse look method, the vector2 object called mouse delta becomes the target mouse delta. Then we can smoothly transition the current mouse delta to the target, pass in the velocity reference and the smooth value. Then we will want to use the smoothed mouse delta to rotate the camera on the local x-axis and the player object on the y-axis. When the player controller starts and stops walking, it's much smoother than it was before, and also the camera movement is now slightly smoothed as well. Of course, if you want to customize these values further, you can do so in the inspector. If we were to walk up this ramp and attempt to walk off the platform, the controller floats in the air, and that's because we haven't applied gravity yet. So this will be the final thing to implement in this episode. Let's discuss how this is going to work. As the controller walks off a ledge, its downward speed will begin at 0, but this value increases while the controller remains in the air, which causes it to accelerate faster as it falls. Once the controller is grounded again, the downward speed resets to 0. So to begin with, I will create a field that represents the gravity value. I'll set the default value of this to be -13, which is a nice value to start with. I'll also create a float variable in the class called velocity y, which will keep track of the downward speed. In the movement function, we will check whether or not the controller is grounded, and if it is, we want to reset the value of velocity y to 0. Just before the velocity vector is constructed, we can define the downward acceleration by adding to velocity y the gravity value multiplied by time.delta time. Finally, just after we multiply the movement direction with the walk speed, we will tag onto the end of this vector3.up multiplied by velocity y. Just remember that gravity works independently of the walk speed, so we don't actually need to multiply it with the walk speed. You may be wondering why I don't use vector3.down for a downwards direction. This is because the value of velocity y is negative, so using vector3.down would actually apply the gravity in an upward direction. So we simply invert this by using vector3.up instead. There are a few other things I'd like to address, like controlling the movement in the air and jumping, but I'll save these for the next episode. I hope you've learned something today and enjoyed this video. Of course, these take a while to put together, so if you'd like to support me, please like the video and subscribe. Thank you so much for watching, and I'll see you soon.